Space, the final frontier. Since the dawn of civilization, humans have looked up at the stars and dreamed of exploring the vast expanse of the cosmos. From ancient myths of gods traversing the heavens to the modern marvels of space exploration, the journey to the stars has captivated our imagination. Why is space travel hard? Space travel is not for the faint of heart. It presents a myriad of challenges, from the unforgiving vacuum of space to the immense distances that must be traversed. Gravity, in particular, poses a significant obstacle, requiring ingenious solutions to overcome its relentless pull. Chapter 1. Fighting Gravity, Rocket Propulsion. At the heart of space travel lies the principle articulated by Sir Isaac Newton centuries ago. For every action, there is an equal and opposite reaction. This fundamental law forms the basis of rocket propulsion, where the expulsion of mass propels a spacecraft forward. Imagine yourself standing on a skateboard holding a heavy object. As you throw the object away from you, you will move in the opposite direction. Similarly, when a rocket expels fuel at high speed through its engines, it generates thrust in the opposite direction, propelling the spacecraft forward through the vacuum of space. Rocket engines come in various forms, each with its unique advantages and disadvantages. Solid rocket engines provide simplicity and reliability, making them ideal for boosters and upper stages. These engines consist of a solid mixture of fuel and oxidizer, ignited by a chemical reaction to produce thrust. Liquid rocket engines, on the other hand, offer greater efficiency and flexibility. They use liquid propellants, such as liquid hydrogen and liquid oxygen, which are stored separately and mixed and burned in a combustion chamber to generate thrust. This allows for precise control of thrust, making liquid engines suitable for main propulsion systems. More exotic propulsion systems, like ion engines, harness the power of electric fields to achieve thrust with remarkable efficiency. Ion engines use electrically charged particles, or ions, to create thrust, offering high specific impulse and low fuel consumption. While they produce low thrust levels, ion engines are ideal for long-duration missions where efficiency is paramount, such as deep space exploration. Thrust is the force generated by a rocket engine, propelling the spacecraft forward. It is measured in pounds or newtons and is essential for overcoming gravity and achieving acceleration. Specific impulse measures the efficiency of a rocket engine, representing the thrust produced per unit of propellant consumed. It is analogous to fuel efficiency in a car and is measured in seconds. Higher specific impulse values indicate greater efficiency, allowing spacecraft to achieve higher velocities with less propellant. By optimizing thrust and specific impulse, engineers can maximize the performance of a spacecraft's propulsion system, enabling missions to explore distant worlds and unlock the mysteries of the universe. Chapter 2. Reaching Orbit, the Art of Trajectories. Achieving orbit is a delicate dance between gravity and velocity. Elliptical orbits, characterized by their elongated shape, allow spacecraft to circumnavigate celestial bodies like Earth while maintaining a stable trajectory. Picture a satellite orbiting Earth. It follows a curved path that brings it close to the planet at one point, periapsis, and far away at another, apoapsis. Reaching orbital velocity is crucial for overcoming the gravitational pull of Earth and entering into orbit around the planet. Orbital velocity is the speed at which a spacecraft must travel to balance the force of gravity and maintain a stable orbit. For Earth, this velocity is approximately 17,500 miles per hour, 28,000 kilometers per hour, or about 5 miles per second, 8 kilometers per second. To reach this speed, rockets must accelerate to incredible velocities during launch, overcoming the pull of Earth's gravity and breaking free from its atmosphere. Launching a spacecraft into orbit is a multi-stage process, each phase carefully choreographed to maximize efficiency and safety. The vertical ascent stage involves lifting the spacecraft off the launch pad and ascending through the dense lower atmosphere. Rockets initially follow a vertical trajectory to minimize air resistance and maximize altitude, gradually pitching over to a horizontal orientation as they gain altitude. The gravity turn maneuver gradually tilts the spacecraft's trajectory to align with its intended orbit, minimizing aerodynamic drag and maximizing altitude. This allows rockets to take advantage of the Earth's rotation and achieve orbital velocity more efficiently. Finally, orbital insertion occurs when the spacecraft reaches the desired velocity and altitude to enter into orbit around Earth. The rocket's upper stage performs a final burn to circularize the orbit, adjusting its trajectory to match the desired orbital parameters. This precise maneuver ensures that the spacecraft remains in orbit for the duration of its mission, whether it's conducting scientific observations, communication, or navigation. Interplanetary travel requires careful planning and precise execution. Hohmann transfer orbits offer an efficient trajectory for transferring between celestial bodies, utilizing the gravitational pull of one planet to propel the spacecraft towards its destination. Imagine throwing a ball into the air. It follows a curved path dictated by gravity, eventually reaching its highest point before falling back down. Similarly, a spacecraft traveling between planets follows a curved trajectory that takes advantage of the gravitational interactions between celestial bodies. A Hohmann transfer orbit is an elliptical path that connects the orbits of two celestial bodies, such as Earth and Mars. By timing the launch and trajectory of the spacecraft, engineers can optimize the transfer orbit to minimize fuel consumption and travel time. This allows spacecraft to travel efficiently between planets, unlocking the potential for exploration and discovery across the solar system. Chapter 3: Life in Space, Spacecraft Systems, Oxygen, Temperature Control, Waste Management. In the harsh environment of space, maintaining life support systems is essential for the survival of astronauts. Oxygen generation systems produce breathable air by electrolyzing water or releasing oxygen from chemical compounds. Temperature control systems regulate the spacecraft's internal climate, preventing extremes of heat and cold that could endanger crew and equipment. Waste management systems ensure the safe disposal of waste products, recycling vital resources like water and organic matter to sustain life in the closed environment of a spacecraft. Solar panels, nuclear batteries, power generation is critical for powering spacecraft systems and instruments. Solar panels harness the energy of the sun, converting sunlight into electricity to power onboard systems like life support, communication, and scientific instruments. In remote locations or during long-duration missions where sunlight is scarce, nuclear batteries provide a reliable source of power. These batteries utilize radioactive decay to generate electricity, providing a continuous supply of energy for essential systems even in the depths of space. Antennas, deep space network, communication, and navigation are essential for maintaining contact with spacecraft and guiding them through the cosmos. Antennas transmit and receive signals between Earth and spacecraft, allowing for real-time communication and data exchange. The Deep Space Network, a global network of ground stations operated by NASA, ESA, and other space agencies, tracks and communicates with spacecraft throughout their journey. By strategically positioning ground stations around the world, the Deep Space Network ensures constant connectivity and navigation support for missions exploring the farthest reaches of space. As missions to space become longer and more ambitious, researchers are developing advanced life support technologies to sustain astronauts for extended durations. Closed-loop life support systems recycle air and water within the spacecraft, minimizing the need for resupply missions and reducing overall mission costs. These systems use processes like electrolysis, filtration, and chemical scrubbing to maintain breathable air and clean water for the crew. Additionally, regenerative life support systems utilize biological processes to produce food, oxygen, and other essential resources, creating self-sustaining ecosystems for long-duration space missions. Bioregenerative systems like hydroponic gardens and algae bioreactors recycle waste products into nutrients for plants, which in turn produce oxygen and food for the crew, ensuring their survival during extended missions to the Moon, Mars, and beyond. Chapter 4: Beyond Earth, Interplanetary Travel. Interplanetary travel often involves utilizing the gravitational pull of celestial bodies to enhance spacecraft trajectories. Slingshot maneuvers, also known as gravity assists, leverage the gravitational forces of planets and moons to gain or lose velocity. By passing close to a planet or moon at high speed and at the right trajectory, spacecraft can utilize the planet's gravity to increase their velocity, allowing them to reach distant destinations with less fuel. This technique has been used in numerous interplanetary missions, such as NASA's Voyager missions, which utilized gravity assists from Jupiter and Saturn to propel the spacecraft out of the solar system. Long-duration missions present unique challenges for astronauts, including exposure to radiation and the physiological effects of microgravity. Radiation shielding systems protect astronauts from harmful cosmic rays and solar radiation, employing materials like lead, polyethylene, and water to absorb and deflect radiation. These shielding systems are essential for protecting crew members during extended missions beyond Earth's protective magnetosphere. Additionally, microgravity effects pose health risks to astronauts, including muscle atrophy, bone density loss, and fluid redistribution. To mitigate these effects, astronauts undergo rigorous exercise regimens and medical monitoring during long-duration missions, ensuring their health and well-being in the harsh environment of space. The future of interplanetary travel holds exciting possibilities with advanced propulsion concepts like ion drives and solar sails. Ion drives utilize electric fields to accelerate ions to high speeds, offering unparalleled efficiency and endurance for long-duration missions. These thrusters produce low thrust but can operate continuously for extended periods, gradually increasing the spacecraft's velocity over time. Solar sails harness the pressure of sunlight to propel spacecraft through the solar system, providing a sustainable and renewable means of propulsion. By deploying large, lightweight sails made of reflective materials like mylar or aluminum, spacecraft can capture photons from the sun and generate thrust without the need for onboard propellant. These innovative propulsion technologies offer new opportunities for exploring the outer reaches of the solar system and beyond, enabling missions to distant worlds and interstellar space. Chapter 5. Returning Home. Atmospheric Re-entry. Returning to Earth from space is a harrowing journey that requires careful planning and execution. Aerobraking maneuvers utilize atmospheric drag to slow down spacecraft and reduce velocity before re-entry. As a spacecraft enters Earth's atmosphere at high speed, it encounters air resistance, causing frictional heating that generates intense heat. Heat shields are crucial components designed to protect the spacecraft and its occupants from the extreme temperatures of re-entry. These shields are made of heat-resistant materials like ablative ceramics, carbon composites, or silica-based tiles that dissipate thermal energy and prevent the spacecraft from burning up during atmospheric entry. By distributing heat away from the spacecraft's exterior, heat shields ensure a safe descent through the Earth's atmosphere and protect the integrity of the spacecraft and its occupants. Atmospheric re-entry subjects spacecraft to extreme temperatures and forces, posing significant risks to astronauts and spacecraft. High-speed re-entry can cause structural damage and thermal degradation, necessitating robust heat shield designs and careful re-entry trajectories to ensure a safe return to Earth. During re-entry, spacecraft experience intense heating as they plow through the Earth's atmosphere at speeds exceeding 25,000 kilometers per hour. This heating can reach temperatures of up to 3,000 degrees Celsius, hot enough to melt steel and damage unprotected spacecraft components. In addition to thermal stresses, high-speed re-entry generates aerodynamic forces that subject the spacecraft to intense pressures and vibrations. To withstand these forces, spacecraft are equipped with sturdy heat shields and structural reinforcements designed to withstand the rigors of atmospheric re-entry. As spacecraft descend through the Earth's atmosphere, parachutes deploy to slow down their descent and provide a gentle landing. Parachutes are essential components of spacecraft recovery systems, allowing vehicles to safely descend from space and land on Earth's surface. The parachutes are deployed at high altitude, where the air is thin enough to allow them to open fully and generate sufficient drag to slow down the spacecraft's descent. Depending on the spacecraft's design and mission profile, parachutes may be deployed in stages, with smaller drogue chutes initially deployed to stabilize the spacecraft, before larger main chutes slow it down for landing. Once the spacecraft reaches lower altitudes, it may employ additional landing systems such as airbags, retro-rockets, or landing legs to cushion its touchdown and ensure a soft landing on solid ground or in the water. Regardless of the landing method used, spacecraft recovery operations are carefully planned and executed to ensure the safe return of astronauts and valuable scientific payloads from space. Conclusion: space travel is a testament to human ingenuity and perseverance, pushing the boundaries of what is possible and inspiring generations to reach for the stars. By understanding the core mechanics of spaceflight, from rocket propulsion to atmospheric re-entry, we gain insight into the challenges and triumphs of exploring the cosmos. As we continue to push the boundaries of space exploration, the dream of reaching new worlds and unlocking the mysteries of the universe remains within our grasp.